Good evening, everyone. I hope I am audible. So let's wait for 5 minutes. If anyone wants to join, can join in the meanwhile. So today we'll be discussing some problems related to the properties of Hilbert space. We'll look at very beautiful characteristics of Hilbert spaces. Okay. Okay, let's start with some true false. State whether the following are true or false. Question number one. Let H be a separable infinite dimensional Hilbert space. Let H be an infinite dimensional, or start with be a separable infinite dimensional Hilbert space, and En be an orthonormal basis basis for H. Then they're saying that the sequence En converges weakly to zero. That is, for every f in H star, Fen converges to 0. Now, since we are in Hilbert space, we know that uh, every functional is something of the form Xen, some inner product type. This should converge to 0 for every x in H. If this holds, then we get the weak convergence. Now, we'll be using the Bessel's inequality to show that this statement is actually true. So, since En is an orthonormal basis, hence an orthonormal sequence, is an orthonormal sequence, or let me write orthonormal basis. This implies by Bessel's inequality, this sum the series summation n from 1 to infinity modulus x en square, this is less than equal to norm x square for every x in H. This implies this, since this series is convergent and this is a series of real numbers, therefore we know that in R the series converges implies the sequence converges to 0. Since the sum is finite, this implies the sequence modulus xen square, this should converge to 0. This implies xen, this converges to 0. Now this is happening for every x in H, which gives us the weak convergence. Therefore, En converges weakly to 0 in H. Therefore, the given statement is true. I hope there is no ambiguity about the solution. If you still have some doubt, you can ask. Okay, if not, let's move to next question. Question number 2. Let H be a Hilbert space and K be a closed convex cone in H, that is, closed convex cone in H with vertex at origin, with vertex at origin, that is, K is closed, 0 belongs to K. If X is belonging to K, then alpha X belongs to K for every alpha positive. That means if we are here, this, suppose we visualize it in some space R2 type. If this point is in K, then this line joining from 0 to this point, the straight line, this whole line should belong to K. Similarly, if some point here, then this whole line is in K. So this is just how you can visualize this space, this cone K. Then they're saying if X and Y are in K and alpha beta are two positive real numbers, positive elements in the field, so taking field to be R, yeah, two real numbers, then alpha X plus beta Y should also belong to K. Let's see if this holds or not. We'll mainly we'll be using the property of mainly we'll be using the convexity of K and the fact that it is a cone. Let's see how. Now let X and Y belongs to K. Now since alpha beta are positive by the definition of cone, alpha X and beta Y also belongs to K. Now since K is convex, alpha X 1 by 2 plus 1 by 2 times beta Y, this should also belong to K. This is just the convex combination. And again, now since this is an element of the cone K, this implies 2 times 1 by 2 alpha X plus 1 by 2 beta Y should also belong to K. Again, because K is a cone, we can just multiply it with by a positive real number. This implies alpha X plus beta Y belongs to K. That is what they were saying. Hence, the given statement is true. I hope this solution is fine. Let's move to next question. Let H be a Hilbert space and K be the closed convex cone as defined above. Let X belongs to H and let for X belonging to H, PKX denote the vector in K closest to X. Then they're saying that the inner product X with PKX should be equal to norm of PKX squared, and the inner product X minus PKX with Y, this is negative, less than equal to 0 for every Y in K. So again, we will be using the convexity of K in order to show that the above statement is true. Solution. Let X belongs to H. Then for this implies obviously PKX, this belongs to K. For any Z belonging to K, we know that since PKX and Z are two elements in the convex set K, so their convex combination must also belong to K. This is T times Z plus 1 minus T times PKX. Kx, this also belongs to K for every T belonging to open interval 0 to 1. In fact, this is closed. Closed interval 0 to 1. This implies norm X minus PKX square. This is, yeah, since this is the shortest distance because pkx is the element which is the nearest. So this is equal to minimum y belonging to k norm x minus y square. Obviously, because pkx is the element in k which is nearest to x, this is less than equal to norm x minus, since this tz plus 1 minus t times pkx is an element in k, this norm, I can write it as norm x minus pkx minus t times z minus pkx. Mm. Now, using the fact that norm x square is basically the inner product of xx, so this is equal to norm x minus pkx square plus t square times norm z minus pkx square minus 2t inner product of x minus pkx with z minus pkx. This implies really these two terms will cancel out. This will give us that this inner product x minus pkx with z minus pkx is less than equal to t by 2 norm z minus pkx square, which obviously tends to 0 as t tends to 0. Therefore, x minus pkx, z minus pkx, this is less than equal to 0 for every z in k. Let's mark this as equation 1. Now, since first holds for every element in k, and it is given that origin 0 belongs to k, since z equals to 0 belongs to k, by first we will get inner product of x minus pkx with minus pkx. This is negative, or this gives us inner product x minus pkx with pkx. This is positive. Also, let me mark this one as equation 2. Also, since z equal to 2 times pkx, since pkx is an element in k and k is a cone, so 2 times pkx is also in k, uh, belongs to k. Again, by equation first, we will get x minus pkx inner product with 2 pkx minus pkx, it's just pkx. This is less than equal to 0. So by second and third, we get the equality. This implies by second and third, this inner product is actually equal to 0, which implies x pkx minus norm pkx whole square is equal to 0. This gives us the first condition that we need to prove. And for the other one, we will use the fact that since z equal to y plus pkx belongs to k for every y in pkx, because in previous question, by question number 2, we know that alpha y plus beta pkx belongs to K for every alpha beta positive, taking alpha equal to beta equal to 1. Now again, by equation first, we get the inner product of x with pk, x minus pkx with um, z minus pkx. So that is just y. This is less than equal to 0 for every y. This is not pkx, this is k. For every y in k. Hence, star is satisfied. Therefore, the given statement is true. I hope this solution is fine. Mainly, we have used the fact that K is a convex set, and using that, this equation first is deduced. This equation first helped us to prove that the setup, the system star is true. Okay, let's move to next question. Let alpha equals to alpha 1, alpha 2, and so on be a sequence in L infinity such that all the terms alpha k's are non-zero for any x equals to x1, x2, and so on belonging to L2. We define Tx to be equal to the sequence alpha 1, x1, alpha 2, x2, and so on. They're saying that then T belongs to T is a bounded linear operator on L2 from L2 to L2, and T is bijective. Let us see whether the statement is true or false. Now for any x in L2, for any x in L2, the L2 norm of Tx, this is square summation k from 1 to infinity alpha k x k square. This is less than equal to m summation k from 1 m square xk square, where m is the maximum of, since alpha is a sequence in L infinity, we will have the supremum. So I should write it as supreme. So which is now this is equal to m square L2 norm of x square. Therefore, Px is less than equal to m times norm x L2. Also clearly, T is linear, and since T is a linear transformation, we get that T belongs to, T is a bounded linear operator from L2 to L2. Now let's see whether it is bijective. Let's start with 1, 1. Suppose x belongs to kernel of T, then Tx is equal to 0. That means alpha k x k is equal to 0 for every k in n. And since alpha k is non-zero for each k, we get xk is equal to 0 for every k in n. So this implies kernel T is singleton 0, hence T is injective. Next, we will see whether it is surjective or not. Now, suppose if y belongs to, now suppose if we prove that the range space range of T is equal to the codomain, that means L2. In that case, we the our linear operator will be surjective and hence bijective. Now, if let's see how the elements of the range space look like. If y belongs to range T, then obviously there exists some x in L2 such that y is equal to alpha 1 x1, alpha 2 x2, and so on. That means each yk is equal to alpha k xk for every k in n. This implies xk is equal to yk by alpha k for every k in n. Now, if I take alpha to be specific sequence 1 by k, taking alpha equals to the sequence alpha k to be equal to 1 by n. Obviously, this belongs to L infinity. We will get y belongs to range t implies xk is, so this is not 1 by, this is 1 by k. Xk is just k times yk. Now since x belongs to L2, we get summation mod xk square to be finite. That is summation k from 1 to infinity kyk square is finite. Now if range t was equal, therefore we can say, or if y belongs to range t, we must have summation k from 1 to infinity kyk square to be finite. Now if range t was equal to, if range t is equal to L2, then the star holds for y equals to 1 by k, because obviously this belongs to L2. Since summation mod 1 by k square, this is finite. This implies by star summation k from 1 to infinity 1, this is finite, but adding 1 infinite times is not a finite sum. This gives us a contradiction. Therefore, range t cannot be equal to the whole space L2. Therefore, t is not bijective. Yeah, because we could find some alpha such that corresponding to that alpha our t cannot be surjective and hence not bijective. Therefore, the given statement is false. I hope this solution is fine. If you have any doubt, please ask. Okay, so if there is no doubt, we can move forward. Move to question number 5. Let H be a Hilbert space and A be a bounded linear operator defined on H. Let NA denotes the null space of A and RA denotes its range. If A is an orthogonal projection, then H can be written as the direct sum of NA and RA. So mainly we'll be using the fact that for a projection mapping, A is equal to A square is equal to A star. That means its adjoint and its square are equal to A. So let's see how we can use that in order to show that this H is direct sum of NA and R. Solution. Let A be an orthogonal projection this implies A square is equal to A. Obviously, because once applied A, for every x, Ax is in this given space. Suppose that we are projecting on some subspace K, Ax will be in K itself. So A applying A again will remain at Ax only. So this is equal to A square is equal to A. Also, uh, since the inner product A star x with any y, this is equal to ax, sorry, x times ay. And since A is projection and ay belongs to K, so this is an element in K and A is in projection on space K. So this is ax, ay, because we know that if A is a orthogonal projection from H to K, then x a sorry xy is equal to axy for every y in K. And since ay is in K, this is equal to ax ay. And again, since ax is in K, this is axy. So therefore, A star is equal to A. Now this implies for any y in range space of A, there exists some x in H such that obviously y is equal to ax. This implies y minus ay, which is equal to y minus a, since y is ax, a of ax, which is y minus a square x. Now, since a square is equal to a, this is just y minus ax. And since y is equal to ax, this is equal to 0. This gives us that y belongs to the null space of identity minus a. This implies range A is a subset of null space of I minus A. Also, if Y belongs to null space of I minus A, uh, then again Y minus A, Y will be 0, which implies Y is equal to AY. And since AY is in range of A, so therefore we get range A is equal to null space of I minus A. We proved this in order to show that our range space is a closed space, because we know that null space is always a closed space. Therefore, from here we get RA is closed. This implies RA closure is equal to RA. Now, uh, we need to show uh, that perpendicular of NA is equal to RA. In that case, obviously, since NA is a closed subspace of H, we can always write H to be the direct sum of NA and NA perp. And if this is equal to RA, then we will be able to prove that this is NA plus RA. That is what we need to show. So, yes. Now, uh, null space of A ka perpendicular. Since A is equal to A star, this is equal to A star perp. We know that this is equal to range A closure. Now, since we have shown that range A closure is equal to range A, this is RA. Therefore, H, which is equal to NA plus NA perp, this is equal to NA plus RA, and hence our given statement is true. I hope this solution is fine. If you have any doubt, please ask. I think there was some disturbance in the network. Yeah, okay. Okay, let's move to next question. Question number 6. Let H be an infinite dimensional Hilbert's. Now we are done with true false. We'll be doing some prove the following or answer the following type of problems. Answer the following. We are on question number 6. Hmm. Let H be an infinite dimensional Hilbert space. And let A from domain of A D E, which is a subset of H to H, be a linear map such that the inner product AX with X, this is less than equal to 0 for every X in domain of A, and I minus A from domain of A to H is surjective. That means onto. Similarly, we will take another operator B from domain of B, which is a subset of H to H, be a linear map such that this inner product Bx with X is less than equal to 0 for every X in BA, and the map I minus B from domain of B to H is surjective. We are also given that domain of A is a subset of domain of B, and Bx is equal to Ax for every, so this is domain of B. This is Bx is equal to Ax for every X in domain of A. We don't know whether we don't know anything about the points that lies outside domain of A and in domain of B. Show that outside also they are equal. So that domain of A is equal to domain of B. Yeah, we'll be using the fact that outside also there will be equal solution. So in order to show that domain of it, in order to show that two sets are equal, we basically show that both are subsets of each other. So one side we are already given. We already have, we already know that dA is a subset of dB. Now we claim that, claim the reverse, domain of B is a subset of domain of A. For that, we will start with some arbitrary element in B, domain of B. That Y belongs to domain of B. Now, since range of B is H, this implies Y minus BY, which is nothing but I minus B at Y. This belongs to H. And since I minus B, sorry, I minus A is surjective. This implies there exists some X in domain of A such that I minus A X is equal to this element in H, which is I minus B Y. So this implies IX minus AX. This is equal to IY minus BY. So this gives us I. Now, since everything is linear, X minus Y minus also since on domain of A, we know that AX is equal to BX. So, and X is in domain of A, so I can replace this AX by BX. So this is BX plus BY is equal to 0. Or we can say that this happens because X belongs to dA, and we know we are given that AX is equal to BX for every X belonging to domain of A. Ix minus Y minus B X minus Y is equal to 0. I minus B and this X minus Y is equal to 0. Let's mark this as equation 1. Now, 0 is equal to, because we know that taking inner product of any non-zero element with 0 is 0. I'll replace this 0 by above in equation 1, because 0 is equal to I minus B at X minus Y. So this is I minus B at X minus Y. X minus Y. This is equal to X minus Y minus B at X minus Y. X minus Y. Now this is equal to norm X minus Y square minus Bx minus Y X minus 1. This is greater than equal to 0, because since clearly this is norm, this is always positive, and this, since X is an element in domain of A, which is a subset of domain of B, Y belongs to domain of B. This implies X minus Y. So this is a subspace, belongs to domain of B. And for every element in domain of B, we know that Bx minus Y in the product with Y. Since we are given that for every element in domain of B. This is domain of B. For every X in domain of B, we have B inner product Bx with X is less than equal to 0. So this inner product is less than equal to 0, and hence its negative will be greater than equal to 0. So these two terms are positive. Sum of two positive terms is positive. So starting from 0, on both the sides we have 0. That means the in between terms were also equal to 0. This implies norm X minus Y square is actually equal to this minus in a product bx minus y with x minus y, this is equal to 0. So sum of two positive terms is 0 if and only if both the terms are 0. This implies norm x minus y square is equal to 0 and this bx minus y, x minus y minus this is equal to 0. So from here, we get x is equal to y. Therefore, y is equal to x. X was an element in domain of A. We started with y being an element in domain of B and ended up getting y being an element in domain of A. Therefore, dP is a subset of dA and hence domain of A is equal to domain of B. In the starting, while writing the question, I said that we'll be using the fact that it is equal outside. That's completely wrong. We do not know how the functions are behaving outside domain of A. But yes, eventually we have shown that domain of A is equal to domain of B. So yes, it's there. AX and BX are equal everywhere. Yeah, that's correct. Hmm. So I hope this solution was fine with everyone. Please go through it once again, and if you have any doubt, you can ask. I'll wait for 2-3 minutes. Okay, if there is no doubt, we can move ahead. Let's move to next question. Even let H be an infinite dimensional Hilbert space. and A defined from D, A subset of H to H, B as in previous question, B as in question number 6, A part, show that A is densely defined, that means DA closure is H. A is densely defined and it is a closed map. That means whenever xn is a sequence in DA such that xn converges to x in H and AXN converges to some y in H, then y is equal to AX. Part B, if in addition A is symmetric, that is the inner product AXY, this is equal to XAY for every XY in domain of A, show that its adjoint A star is equal to A. Solution. Firstly, in order to show that the operator A is densely defined, we need to show that DA closure is equal to H, or if we show that the perpendicular of DA is singleton 0, and since DA is a subspace of H, this will show that its closure is equal to H. We know that uh, if a subspace has its perpendicular singleton 0, in that case its closure is the whole space. Now so we claim that dA per is singleton 0. Let X belongs to dA per, which is obviously a subset of H. Let. Now, since I minus A is surjective, this is as it was defined earlier, I minus A is surjective. This implies there exists some Y in domain of A. Since this X is an element in H, which is the codomain of I minus A, and since I minus A is surjective, so that means X is in range of I minus A. That means there exists some elements, its preimage in domain of A, such that this X is equal to I minus A at Y. This implies norm Y square minus inner product ky with y. This is nothing but I minus a y. This is equal to xy. Now, since y is an element in domain of A and x is in its perpendicular, so this inner product is 0. X belongs to B per orthogonal and y belongs to orthogonal complement. X, since x belongs to the orthogonal complement of Dn. Now, this gives us, now since a y, this is less than equal to 0 for every y in domain of A, Again, as we did earlier, 0 is equal to norm by square a by y. This is, and if this was not even required, this is greater than equal to norm by square. Yes, because negative of minus a by y is greater than equal to 0. And since norm is always positive, so this implies norm by square or just the norm by is equal to 0, and this implies y is 0. I need to show that x is 0. This implies 0 is equal to norm by square, which is equal to a by y. So this implies norm by square is equal to 0, implies y is 0. This implies now x is equal to, yeah, x is equal to I minus a by, this is 0 minus a at 0. And since a is a linear operator, a at 0 should be 0. X is 0. Therefore, dA per is equal to 0. Hence, dA closure is equal to h. Therefore, A is densely defined. Now we need to show that A is closed. Let Xn be a sequence in dA such that Xn converges to some X in H and AXn converges to some Y in H, H to H. If we show that AX is equal to Y, Ax is equal to y, we'll get that A is a closed map. So we need to show that y is equal to Ax. Now since the sequence xn minus Axn, this converges to x minus y by direct basic algebra of limit of sequences. Let Zn be the sequence xn minus Axn. This is the sequence in H. We get that Zn converges to x minus 5. Now, since x minus y is an element in H and I minus a is surjective, this implies there exists some vector v in domain of A such that I minus a v is equal to x minus y, or v minus a v is equal to x minus y. This implies xn minus v minus a at xn minus v. This is nothing but xn minus axn minus v minus av is equal to zn minus x minus y. And this implies norm xn minus v square minus the inner product of a x n minus b with x n minus v. This is equal to, this is x n minus v minus a x n minus v. This one is 1. So this is equal to inner product with x n minus v. So by first, this is equal to zn minus x minus y, xn minus, this is by first. Now this is less than equal to, obviously every real number is less than equal to its modulus. And by Cauchy spots, this is less than equal to norm zn minus x minus y, norm xn minus y. So this implies 0, which is greater than equal to a xn minus v with xn minus v, because xn minus v, this belongs to domain of A. Each xn is in domain of A, v is also in domain of A. And for every vector y in domain of A, we know that this inner product a y is less than equal to 0. This, and from above, let's mark this as equation 2. By equation 2, this is greater than, not equation, by inequality 2, this is greater than equal to norm xn minus v square minus norm zn minus x minus y, norm xn minus v. So this implies norm xn minus v times norm zn minus x minus y. This is less than equal to norm xn minus v, greater than minus v square. So this terms gets cancelled out. This implies norm xn minus v less than equal to norm zn minus x minus y. Now, since zn converges to x minus y, this tends to 0 as n tends to infinity. So this implies xn converges to v in h. Also, we started with xn converges to x in h. So by uniqueness of limit, we get x is equal to v, which belongs to domain of A. This implies x is an element in domain of A, and we know that, and this will give us, oh, sorry, I should write, this implies x minus ax is nothing but v minus av, which is, yeah, because v is equal to ax, and this is equal to, so we should keep this x as it is, x minus av, and we know that a second. Yeah, from here, v minus av is equal to x minus y. Let's mark this as some one. This is v minus av, which is equal to x minus y by hash 1 So this implies y is equal to ax. Hence, the given operator A is closed. I hope this part A is fine. Please go through the proof once again. If you have any doubt, please let me know. I'll wait for 2-3 minutes. After that, we'll move to part B, where we will be showing that if A is symmetric as well, in that case, A is equal to its adjoint. That will not take much time. Yeah, please go through this proof again. Uh, how we prove that A is closed and densely defined. Okay, then let's move to part B. We need to show that if A is symmetric as well, that means it satisfies such equation, then it is equal to its adjoint. Part B. Let X belongs to domain of A, then for every Y belonging to domain of A, we have modulus xy xay, sorry, xay. This is equal to axy by symmetry. This is less than equal to norm ax, norm y. This implies, by the definition, I would like you to go back to the previous sessions where we discussed how the domain of the adjoint operator is defined. Hello? Okay. So I would like you to go back to the previous lectures. Yes. Go back to the previous lectures and see how we define the domain of the adjoint operator. So from there, you will get that this X belongs to domain of A star. Therefore, for we started with X in domain of A, we got X in domain of A star. This gives us domain of A is a subset of domain of A star. Also, this inner product A star X with Y, this is equal to A X A Y. Just by since this is the property of A star, and this is equal to AXY because this is we are given by symmetry, and this is happening for every Y in domain of A and X belonging to domain of A, which is a subset of domain of A star. This implies A star X is equal to AX for every X belonging to domain of A. Now we'll show that domain of A is equal to domain of A star. Because on domain of A already we know that A is equal to A star. We claim that domain of A is equal to domain of A star. Clearly, if we show that this, then by this is equation number 3. Then by this equation 3, we will directly be able to show that A is equal to A star. So already we have one side containment. That means dA is a subset of dA star. All we need to show is that dA star is a subset of D. So let's start with an element in dA star. Let X belongs to dA star be arbitrary. So, and let Y belongs to H. This implies there exists some Z in dA such that I minus A Z is equal to Y because I minus A is surjective. So this implies the inner product X minus A star X with Z, this is equal to I minus A star X Z. So by properties or characterization of adjoint, this is I minus A star Z, which is equal to X, since A star is I and A star is A, I minus A Z, which is equal to Y. Now let W be an element in domain of A be such that W belonging to domain of A be such that I minus A W is equal to X minus A star X, obviously because X minus A star X is an element in H and I minus A is surjective. We can find such W. So this implies the inner product X with Y. This is equal to inner product X minus A star X. I'll replace it by W minus AW with Z. This is equal to now since W is an element in domain of A and in domain of A we have already proved that A star x is equal to ax. So I can replace this a by a star. This is a star w z. Since w belongs to domain of A, by equation third, a w is equal to a star w. This is equal to, yeah, this is I minus a star w z, which is equal to w I minus a star star z, which is equal to w I minus a at z, and I minus a at z, I minus a at z is equal to y. This is w and y for every y in h. Therefore, what we got? We got xy, this inner product, is equal to wy for every y in h. That means x is equal to w, which belongs to domain of A. That means x is an element in domain of A. We started with x in domain of A star. We got x is in domain of A. That means domain of A star is equal to. That is what we needed to prove. Hence, A is equal to A star. Please go through this solution once again. If you have any doubt, please ask. There are a bit of things that one needs to remember why we are doing all these things. So eventually, in order to get domain of A star is equal to domain of A, because we have already seen that on the domain of A star is equal to A. All we need to show is that the domain of A star is domain of A itself. So for that, we need to do some technical things, not that much, but yeah, uh, yeah, go through it once again. If you have doubt, you can ask. Okay, let's move to next question. This is question number 8. Let H be an infinite dimensional Hilbert space. And let En from 1 to infinity be an orthonormal basis for H. Let C be a sequence C1, C2, so on, and L2. Define Xn equals to summation k from 1 to n Ck Ek. Show that the sequence Xn is a Cauchy sequence. N is a Cauchy sequence. Found P. Show that there exists unique X in H. There exists unique X in H such that X is equal to summation k from 1 to infinity Ck Ek. And part C, deduce that every separable infinite dimensional Hilbert space, deduce that every separable infinite dimensional Hilbert space is isometrically isomorphic to L2. That means for any separable infinite dimensional Hilbert space, there exists an isometry which is bijective from H to L2. Solution. Let's start with part A. Let n and m be some natural numbers. We need to show that this sequence is Cauchy. That means norm xn minus xm tends to 0 as nm goes to infinity. Let n and m be two arbitrary natural numbers without loss of generality. Let n be strictly greater than m. Then norm xn minus xm is square. This is equal to norm of. So by definition of xn, we can see that eventually this is summation k from m plus 1 to n, because rest of the terms will be cancelled out. Ck Ek. And since Ek's are orthonormal, this norm is equal to summation k from m plus 1 to n mod Ck square. Now this, since C is in L2, that means summation Ck square is finite. So as for m and n large, this sum is actually the tail of a convergent series, which will converge to 0 as n and m tends to infinity. Since C belongs to L2, this implies summation mod Ck square. This is finite, and we know that tail of a convergent series is converges to 0. Therefore, the sequence xn is Cauchy. Now we need to show that there exists unique x in H such that x is equal to this. Um, yes, this sequence xn, since each ek is an element in ek times ek. Okay. So let if possible, there exists some x and y. Let if possible, there exists x not equal to y such that both are equal to this sum. That means x is equal to summation k from 1 to infinity ck ek. This is equal to 1. Now, since ek is orthonormal basis and x is an element in the Hilbert space H, this implies x is equal to summation k from 1 to infinity this inner product x with ck times ek. This implies c for every k, ck is nothing but inner product of x with ck. Similarly, similarly, ck is equal to inner product y with ck. Sorry, ek. Okay. So, because ek is the orthonormal basis. Hmm. So this implies this inner product is equal for every k. That means obviously the sum will also be same, which is an expression for x equal to y, which gives us a contradiction. Therefore, there exists unique x in H such that x is equal to summation k from 1 to infinity ck. Also, since xn is a Cauchy sequence in H, it is H is a Hilbert space. It is it must be convergent. Therefore, this limit should exist, and now we have proved that the limit is unique. Yes. Yes. Hello. You can write in the chat box if you need to say something. Do you have some doubt?
No, ma'am.
Okay. Yeah. This implies there exists at least one x in H such that x is equal to limit n tending to infinity xn, which is nothing but summation k from 1 to infinity xk, sorry, ck ek. In fact, since we know that this limit is always unique, so it should be unique. So there was not much need of this part B. Let's move to part C. we need to show there exists some isometry. Now let H be some H be an H be a separable infinite dimensional Hilbert space. H be an arbitrary separable Hilbert space. Then we know that it has a countable orthonormal basis. It has a countable orthonormal basis. This implies there exists a sequence En, or we can write it as Ek, such that it is a basis for H. That is, for every x in H, x can be written as summation x ek a from 1 to infinity. Now define T from H to L2. T of x is equal to the sequence Ck. So this is equal to C, where T is equal to the sequence Ck, where each Ck is just inner product x with Ek. Clearly, Tx belongs to L2, since norm Tx, L2 norm, this is equal to summation k from 1 to infinity mod Ck square. This is summation k from 1 to infinity mod x Ek square, which is norm of x, which is finite. This is less than equal to by Bessel's inequality. So therefore, Tx belongs to L2, and this T is an isomer. In fact, you can see this, that norm Tx will be equal to norm x. Therefore, T is an isometry. Moreover, by above properties, we can directly see that it is a bijection as well. Okay, let's move to the last problem of this session. Question number, so this is question number 9. Let H be an infinite dimensional Hilbert space. And En be an orthonormal sequence orthonormal sequence in H, let lambda n from 1 to infinity be a bounded sequence of real numbers. Now define an operator A for any x in H. We define Ax is equal to summation n from 1 to infinity lambda n in a product of x with en times en. So that A is well defined and is a bounded linear operator on H. So that A is well defined and belongs to the space of bounded linear operators on H. This A is well defined if this limit is finite for every x solution. For some x in H, let y is equal to summation n from 1 to infinity lambda n x en. Now this A is well defined if this y, this sum is finite. If limit n tending to infinity, summation k from 1 to n, lambda k, x ek, which is equal to summation n from 1 to infinity, lambda n, x en is finite for every x in H. Yeah, we don't need this. Now, for any n in n, for n in n, define yn to be the sum k from 1 to n, lambda k, x ek. Now, if we show that the sequence yn is convergent, then we will be done. So, in order to show that it is convergent, we will prove that it is Cauchy. Now, since it is a sequence in Hilbert space H, so Cauchy will imply a convergent. Now, without loss of generality, let n is greater than m, then norm yn minus ym, this is equal to square. This is equal to summation k from m plus 1 to n, sorry, m plus 1 to n mod lambda k square x ek square. Now, since lambda k, the sequence lambda k is a bounded sequence, it will have an upper bound. So I can write it less than equal to some m square summation k from m plus 1 to n square. Now, this is less than equal to norm x square. Or not norm x square. Now, since no, this sum since this sum is less than equal to norm x square, which is finite, therefore this sum is finite. So its tail, now because this is a tail of a convergent series, this will converge to 0 as n and m tends to infinity, because summation n from 1 to infinity mod x ek square, this will be less than equal to norm x square, again by Bessel's inequality, which is finite. Therefore, its state will converge to 0. This implies this yn is Cauchy in Hilbert space H. This implies yn is convergent. This implies summation n from 1 to infinity. This was lambda n x en. The sum is finite. Therefore, A is well defined. Also, we can see that now we need to show that it is clearly it is a linear transformation. All we need to show is that it is continuous or it is bounded as well. So this AX is equal to limit n tending to infinity summation k from 1 to n. So we need to show it's L2 norm. No? L2 norm of AX, not L2 norm. We are in H. AX norm square. Now this is less than equal to, as we have done above. You can see that this is less than equal to m square summation k from n from 1 to infinity mod x n square, just using the fact that lambda n is a bounded sequence and the definition of the operator a. This is less than equal to m square times norm x square. Therefore, ax square, ax, this is less than equal to m times norm x. Hence, this a is a bounded linear operator on H. Well-defined bounded linear operator on H. Hence, we are done. So if you have any doubt, you can ask. Alright, we can finish this session now. Next session will be on next Wednesday. That will be our last session. After that, I think you have exams. So, okay, we'll meet next Wednesday. Coming
Thank you.
Wednesday. Okay.